It's a okay. It's a pleasure to once again have the opportunity to talk to everybody. Unfortunately, last time I did this live, I did it at UT, and the internet crashed, as you may recall. So I recorded that lecture and sent it to you. I'm going to talk about a different topic today, or a different set of topics, and although it will have some overlap with what I talked about in April. And by the way, over the more or less 3 years of COVID, every time I gave a Zoom lecture, I did it in my house, except that one time at UT, and that was the only time I had an internet crash. So hopefully everything will work today just fine. All right, the title of my talk is The Finite Element Method in Computational Mechanics. I'm going to talk about the history, the past, the present, and the future. Okay, let's see. I have to do it this way. All right, so just an outline. I'm going to focus on when the finite element method began. I will talk about the present. It has attained enormous success, as you know, but there's still some issues, and that'll bring me to the topic that I devoted my lecture to in April, isogeometric analysis. And I'll just say some brief things, just recall some brief things to sort of put you in the place where you can understand what will be coming thereafter. So I'll do a brief review of concepts, very brief, in fact. I talked about mathematical perspectives in the spring. I focused on functional analysis and spectral analysis and mentioned the variation diminishing properties. I'll just very briefly go through that again, say a couple of different words about it. I mentioned Kagarov n-widths. I didn't talk about that in the spring, but I thought I would present those ideas today, because they're another way of evaluating discrete methods and comparing them to others. And it's a very nice methodology. And again, it has shed light on isogeometric analysis as well as finite element analysis. In the spring, I talked about modeling paradigms, boundary fitted modeling and immerse modeling. Boundary fitted is classical. It's been going on in finite elements and isogeometric analysis for quite some time, of course. I'm going to focus on immerse modeling and show you some new applications that you didn't see before. And then we'll talk about the future and what may be happening as we go forward with these methods, finite element and computational mechanics, of course. So the past, and the question is, when did the finite element method begin? Well, I like to put the place of its beginning with Alexander Renikoff. You may or may not have heard, well, maybe you haven't heard about him, but he was very influential early on. He wrote a thesis at MIT in 1940, and what he did was to solve problems in elasticity in his thesis with framework analogies. And the interesting thing about that is, as you go forward, that was developed in many places and really was a precursor to finite elements in engineering. And in fact, the second job I had after I graduated with a mechanical engineering degree was at General Dynamics Electric Boat in Groton, Connecticut, where they make submarines. And there was a group that utilized his methodology. I had to study all of that and learn it thoroughly. And at the time, this was like 1967, the matrix methods of structural mechanics, at least with beam elements, was well established. There were codes, and they had the architecture of contemporary finite element codes, exactly the same architecture. And they used these lattice analogies to model shells and plates and structures. We had whole models of the complete hulls of submarines at that time. And they were calculating in the mid-1960s over 10,000 degree of freedom systems. They had computers. And when I started my career with my first job as a design engineer, there was not a computer to be seen in the design office. And that was in 1965. But in General Dynamics, in the research lab, there were computers. They had a UNIVAC 1108. It was a supercomputer of its day. It had an enormous drum, but very, very little core memory. So you had to pass all information in and out as you were solving problems. But anyway, I worked on this boat, in fact, with this methodology. It was rather sophisticated and very interesting. One of the things that they like to talk about there is actually the group had a consulting job with the World's Fair group that was planning the World's Fair for 1964 in Queens, New York, in Flushing Meadows. And the landscape architect, Gilmore Clark, who designed this and called it the Unisphere, it was sort of the symbol of that World's Fair. I've been there. I was there many times. I was living in New York at the time, so I could see it nearby in Brooklyn. And it's interesting, if you go to the website that I indicated below, it says, engineering the immense structure involves solving hundreds of simultaneous equations, hundreds, which is nothing now, even thousands is nothing, but anyway, facilitated by computers used to design atomic submarines. And indeed, the analysis of this was done at General Dynamics Electric Boat using the Renikoff method, and it is still standing. It's had some refurbishing over the years, but it's there. It's quite an impressive thing to see, as you can see from the photograph. So that occurred, and many people later on, as you'll see, that did more, let's say, conventionally begin finite element work, spoke to the Renikoff method as the precursor and an inspiration. But in the mathematics world, there is a paper of Courant that was an extremely prescient paper, although it seemed to not attract an enormous amount of attention at the time. It was published in 1943. It was based on a talk in 1941, presented at a meeting of the American Mathematics Society. And about a year later, a little over a year later, Courant delivered the paper that corresponded to the talk, but he added an appendix to that paper. And the appendix was titled Numerical Treatment of the Plane Torsion Problem for Multiply Connected Domains. And he mentions this was not contained in the original address. And these are some pictures from that paper. And what he did is he solved the torsion problem, which involves a Laplace operator. And the discretization, the variationally inspired discretization, was with linear triangles, the classical two-dimensional basic finite element, the linear triangle. And it appeared in the appendix of that paper. And he even used the word elements in that paper. He said, of course, one must not expect good results from a method using so few elements. And as I said, this paper just disappeared. It was rediscovered in the late 1960s in what had already become a finite element community, both in mathematics and in engineering. It did attract some attention earlier, but not for this. It attracted attention because in this same paper, the penalty method was developed, which has had impact in analysis, of course, but its initial impact was in optimization. So it's a very interesting paper, and it's very clear and beautifully written, and anyone that reads it today can fully appreciate it, I would say. But in engineering, in the 1950s is when finite elements really began to take off, both in Europe and in the US. The activity was in the aerospace community. There was a lot of important research going on in aerospace at the time, and they had to analyze swept back wings, and more complicated geometries and various other things. But John Argyris, who was at Imperial College in London and then at the University of Stuttgart in Germany, where he had an enormous institute, 150 people working for him. And he was on the case. He wrote a series of articles in a journal called Aircraft Engineering in 1954 and 55, and beautiful presentations of the competing methods at the time in the way of matrix analysis of structures, the force method and the displacement method. And he at the end of that article, had a panel And the panel was essentially the 4-node quadrilateral finite element, in essence. And Ray Clough in the United States worked with a top research group in Boeing. He used to do that in the summers, led by John Turner, who was a legendary researcher at Boeing. And obviously, Ray Clough was no slouch, as you can see here. Harold Martin was a famous professor at the University of Washington. And these people were working on developing methods, and they also sort of discovered independently the linear triangle, and they did dynamics and a number of other things. It was Clough that named the finite element method. But this really got things going. Now, the interesting thing is Argyris was an aircraft structural engineer by training. Clough was a civil engineer. And this research on finite elements, it began in the aerospace institutes and laboratories. It really facilitated this whole idea of the finite element method because they had computers. And most places didn't have computers until much later. And now, so computers is at the essence of the rise of the finite element method. Everybody's familiar with Moore's law. It's slowed down a little bit. We're getting sort of a double of integrated circuits every 2 years now, but it's continuing and will continue for a while, but apparently not economically. The cost per chip has stopped falling. But there's tremendous investment in chip fabs. Samsung is building a facility right now in Taylor, Texas, which is right near Austin, a $17 billion facility. And they plan to spend $200 billion in this area on several fabs over the next decade. Taiwan Semiconductor is spending $40 to $44 billion this year. They're the big company in this area. Now, so that's becoming daunting, obviously, the cost involved, but there are other ways to get better performance. Parallel processing is now ubiquitous, as are GPUs, graphical processing units, which really started out in the rendering of images, and now they're everywhere and everything. And they're used in large-scale computation because you can really speed up things with GPUs. And also, sort of new in the game a little bit is custom chips. Apple's custom chip. Now, the M1 Max has 57 billion transistors on one chip. So it's getting to the number of transistors are approaching the number of neurons in neurons in the brain. One of the really important figures in the history of finite elements analysis was Oleg Zienkiewicz. He was another civil engineer. And it was Clough, who was a civil engineer, who convinced Zienkiewicz to pursue the finite element method. Zienkiewicz had worked with Southwell in England, and they did finite difference type work. But once he got hooked, he became the main promoter of finite elements around the world. And I first met him in 1967. I went to a lecture that he was giving at MIT. I took the train from Groton, Connecticut. And he presented this slide, which actually, it kind of stunned me, but it kind of put in my mind, well, gee, with finite elements, you could model anything, you know? You could even model maybe a human being. The finite element guy, it just seemed to extend the notion of what you might do with these very structured methods of the past. But he was all over the place. They used to say at Swansea, what's the little joke was, what's the difference between God and Zienkiewicz? And the answer was, God is everywhere, but Zienkiewicz is everywhere, except Swansea, where his institute was. Now, one of the things that Zienkiewicz did, he was sort of an empire builder, and he recognized talent, and he tried to bring it to Swansea. And the main person that he brought there was a Rolls-Royce engineer who was also working on aerospace problems at Rolls-Royce, named Bruce Irons. And so he brought Bruce Irons to Swansea, and they had an enormous period of productivity. And Bruce Irons was clearly one of the most creative minds in the early days of finite elements. He was a true quiet genius. He developed the isoparametric finite element concept, which is very close to the ideas of computational geometry that underpin isogeometric analysis, numerically integrated elements, shape functions, subroutines, the way everybody does everything nowadays, the patch test, just sort of a mathematical test that you can actually compute to show if an element is coded correctly and well formulated mathematically. Frontal solvers, which are still the main direct solvers, serendipity elements, the solid shell element concept, semi-lift shell element. This man was truly a genius. He was a very, very quiet personality, and he was diametrically opposite Sienkiewicz, who was a very vivacious type personality. And they fell out after a while, and Irons became a professor at the University of Calgary and then had a very sad end to his life. Actually, the finite element method had some push in the mid-1960s in China as well. Kang Feng, who was considered the father of Chinese computational mathematics, wrote a very important paper in 1965 entitled Finite Difference Method based on variational principles. He really had the idea. He was very influenced by, I'd say, the variational methodology that was appearing in Russia at the time, books of Miklin, for example. And he wrote an article that also had the basic ideas, and he was interested in approximation theory and doing proofs. He had a couple of student postdocs, I was told, by some of my Chinese students and postdocs. Apparently, this little small group who were working with him, they all fell out and didn't get along, so they all sort of split up. And they were doing computing, and then, of course, later on, the Cultural Revolution came along. So that kind of stopped research in finite elements in China for a while. But there's a very nice history, and it was written by actually my first PhD student when I was at Caltech, Wing-Kiam Liu. And this is where I found out about Kang Feng. So I would recommend that to you. You could get that off this slide, which was just recently published. This is his work that was, this is a page from that original paper, and this is a book that was published in 1981, a revised edition of the original. So you can get some insight to what was going on in China at that time. So the finite element method went from aero to civil and then to mechanical. The emphasis went from aerospace to civil in the 1960s. The mathematical theory of the finite element method began in the mid to late 60s. In the 1970s and thereafter, the major area of application and development and commercialization was in mechanical engineering. And that really began the era of computational mechanics, where we were trying to infuse algorithms with deep knowledge of mechanics. Many commercial codes, I'll say a little bit about a couple of them later on. In the 1980s, fluid dynamics became a big application area. We developed methods that actually worked for fluids, unlike the initial finite element methods that were not mathematically well conceived for these problems. But that became sort of a boom, and there were numerous applications of this technology now in fluids and solids and engineering science and mathematics. Then in the 1990s, medical imaging modalities became much more sophisticated, and that provided a basis for patient-specific anatomic modeling and application of the finite element method. So computational medicine is now a big area. If you want to get a glimpse, another glimpse of the history of the finite element method and computational mechanics, we recently put out a 50th anniversary special edition of Computer Methods in Applied Mechanics and Engineering. This is sort of the leading journal in the field. It really is a journal that over these years, at least while I was editor for the last 43 years, it has really spanned engineering to mathematics and every linear combination in between. So what you can do if you go there too, you don't need a subscription or anything like that. It's wide open. You can download the 50 most cited papers and a brief historical article that the three of us wrote, myself and Actually, myself and my co-editor, Manolis Papadrakakis, Tarek Zodi just joined when Tinsley Yoden retired a year ago. So this year I'm stepping down too. Long story, but I will be stepping down as editor as well. But in any event, if you're interested in the history, as you can deduce it from the papers that are highly cited, it's in that journal. So let's move to the present, skip over a lot of things. Cars are designed on computers with the finite element method. Airplanes are designed on computers with the finite element method. Now that we have, since the 1980s, stable and accurate methods. And the nice thing about the computational mechanics basis of the method is that fluids and solids can be integrated in analysis capabilities in a very, very I would say, homogeneous way. In some sense, there's no difference. So they're just mechanics with different PDEs, but they can be joined very, very nicely. So this is a fluid structure interaction analysis of a full body model of the arterial system. It was put together by Alberto Figueroa at the University of Michigan. It's hard to see the motion, but it's there. It looks like it's just a stick-like model of one-dimensional elements, but it's fully three-dimensional. The material properties of the arterial wall are spatially varying to reflect true physiology. That's just a detailed picture of the type of resolution. That is the surface, and those are prismatic triangular elements that go in one layer. That's the wall model. Then inside is a tetrahedral model with boundary layer refinement to get the Navier-Stokes solution correct. Full Navier-Stokes calculation. So the finite element method is an enormous success. Now, why? Now, most people say, well, you can do arbitrary geometries. That's true, but I would say you can do arbitrary topologies. The finite element method in some ways butches geometry, and I'll make that point in a little while, but it can do arbitrary topologies, which is a big advantage, of course. I would say that two of the reasons are simplicity and generality. The same basic concept pertains to everything. A method consists of spaces of functions and a variational method. Okay, those are the two ingredients. You put those together and magic happens. The other reason for success is general purpose computer programs. What started in structures has now expanded to just about every physical domain you can think of in science and engineering and medicine. And all of that can reside in one large computer program like LS-DYNA, something like that, that's used throughout all of these disciplines. And finally, a firm mathematical basis. It's hard to beat these methods. They really have a strong, convincing mathematical basis, and that is the underpinning. But like with everything, the search for better methodology goes on. There are still problems with the finite element method, and some of them are a little bit exterior. One is model creation. To create a finite element mesh from the source of data, namely a geometric CAD file from computer-aided design, or from, let's say, a CT image in medical applications, you have to translate one form of data to another. That induces geometry errors because the translation requires features to be removed in order to generate the mesh, geometry cleanup. These files are not pristine. They have flaws. You need to correct those in order to generate a finite element model. So that's a big problem. And actually, that was a problem that really started to intrigue me about 20 years ago. The other is the promise of higher order finite elements has never been realized in applications. There is an over-reliance on very low order elements. You might wonder why from the academic literature, but that is the case. And there are good reasons why. And I'll sketch some of those reasons a little bit later. Also, closing the loop with design optimization. You develop a finite element model, it has no connection to the geometry that was its underpinning, namely, say, the CAD geometry. So if you want to optimize the design, you have to go back to CAD. There's no connection anymore. So everything has to be translated essentially in some manual way. So that's another problem. So why is it so complicated to develop finite element meshes from CAD? Let's take a look. This is a simple piece of a B-pillar, a Honda. This B-pillar is just one piece of metal of the assembly. It's been cut, shaped, and it's been, this is my phone. Unfortunately, it's popping up on my computer. Sorry about that. It'll end. And this has holes drilled in it too. So one little piece of metal, that should be easy to generate a finite element mesh for that. But you have to do lots of things. You have to clean up the file. You have to remove some of the small features because you can't mesh them. And the fact is, the issue here is really the data structure. The picture looks just like you'd expect it to look. But the data structure that generates that picture is much more complicated. That little guy involves the images of 1,280 patches. These are trimmed surfaces. A patch is mapped into the design. You see these rectangles being mapped in here. And then the part that is really not part of the design, you just trim it away. And the intersection lines are not watertight. You might say, why don't you do that? Well, most CAD is done with cubic splines. The intersections of two curved cubic splines surfaces is a degree 324 polynomial. That's why they don't do that exactly. So you have a lot of gaps and overlaps in the models, and they need to be fixed to generate meshes. So I'd like you to think about CAD as consisting of patches that involve static binary phase fields. And by that, I mean that where the material is, as in that's phase 1, has a value 1, and where it's cut away, that's phase 0. Okay. We'll see that this concept of phase fields pops up all over the place. Now, you see how complicated things could be with that little piece of metal. Just imagine these CAD files and building a detailed finite element model from them with all the features, the bolts, the holes, all the fine scale features. Can you imagine? It's very complicated, and it just can't be done practically. So what people do is they remove a lot of these features, and that has consequences with respect to accuracy. So the objectives of my research about 20 years ago was to try to tie finite element analysis within CAD geometry. These two fields of computer-aided geometric design and CAD and the finite element field grew up completely independently, and they just didn't talk to each other really. So what I wanted to do is go back and see if I could generate a finite element technology that would reside within CAD, and therefore it would simplify this model development problem, and we could integrate design and analysis. So that was the idea of isogeometric analysis. And as I pointed out in the spring, this is sort of a recent set of data from Web of Science. If you put in isogeometric analysis, starting with the first paper that we wrote in 2005, you can see the papers getting up into the 500s a year. And the citations last year were over 18,000. This year it's got a way to go yet, of course. And there are over 4,000 papers and 97,000 citations so far. So it's a, you know, it's had some impact, obviously. So what is it? It's based on computational geometry technologies, NURBS, T-splines, U-splines, things that are used in design, animation, graphic art, visualization. And I think people in analysis would be surprised, but those technologies are much richer than the polynomial-based finite elements that have been used for years and years and years, since the 1960s, I would say. And what these technologies facilitate is precise and efficient geometric modeling, obviously, simplified mesh refinement schemes with some advantages. Smooth basis functions with compact support. You can build smooth objects. That means you can use those basis functions to solve higher order PDEs without any complexity, in fact, very simply. And superior approximation properties. Let me emphasize, much superior approximation properties. But the big goal was to integrate design and analysis. So that's what's been going on. So if you think of it, though, as a generalization of the finite element method, which you can indeed think of it as, you have different refinement schemes in finite element analysis to achieve better results. H refinement, mesh refinement, that is. P refinement, polynomial refinement on a fixed mesh. You can do the same things in isogeometric analysis with all these technologies, but you can also do something called K refinement, which you increase the order of the, let's say, the underlying polynomials, but you can also increase the smoothness globally. So B-splines and NURBS, quickly, just for those who haven't seen anything like this before. B-splines are the progenitors of just about everything in computer-aided geometric design. They can be defined recursively by the Cox-de Boer recursion. If you have what's called a uniform knot vector, this is sort of your one-dimensional patch, 0 to 5. You have a uniform knot vector. You start off with constants on each knot span. Then recursively, you take the constants and go to linears. That looks just like linear finite elements, and it is. And then these recursively go to quadratics. But as soon as you hit the quadratics, you get a completely different type of basis that's been different than the one that's been used in finite element analysis, namely the Lagrange interpolatory basis. This one is smooth, as you can see. This one is C1. If we went to cubics, the natural one would be spanning another knot span, and it would be C2 continuous, and so on and so forth. These are pointwise positive as well. If you take a basis like this, what you can do is you can actually repeat knots and control continuity. So this is quadratic. This is the basic C1 quadratic basis function in green. But if you repeat this knot, you will drop the continuity from C1 to C0 here. And whenever you see 0, you are interpolatory. This basis will interpolate at those 3 points. This is called an open non-uniform knot vector. Open means you have multiplicity p+1 knots at each extremity of the patch. And that is just facilitated by this definition of the knot vector from which everything unfolds. If you take that basis and multiply it by coordinates, control points, you get this object. And you can see that you're in general not interpolatory, but you're smooth everywhere except for this C0 point. This is kind of the designer view. If you tug on the control point, you change the shape. But because of the properties of these functions, you will change the shape monotonically without ever introducing oscillations. And that is absolutely essential for design. Now, there is a dual point of view here, and it's really the finite element point of view. You can deconstruct this into so-called Bezier elements, which are like the typical elements of finite element analysis on the right. So you have 5 elements. Those are the images of the domains of the patch, the element domains. Say 0 to 1 is here, 1 to 2 is here. So those are the elements. But notice in this decomposition, that's exactly the same geometry. Okay, so your element file is living on your exact geometry. And you can refine the mesh if you like for analysis, but you refine the mesh without changing the geometry. The refinement is embedded in the geometry, unlike classical finite element analysis. So what we've done is we've just inserted knots at all the midpoints here, and we have a finer mesh, more basis functions on exactly the same geometry. And you can do it to your heart's content, as you see here. Now, the most important tool, I would say, in CAD design, beyond B-splines, are rational B-splines, where you take their ratios. And the good thing about rational B-splines is you can make use of certain facts about conics and B-splines and higher dimensional spaces and projection, projective transformations. And with them, you can get explicit formulas that represent all conic sections, circles, ellipses. These are NURBS objects right here. And that precision, of course, is essential for engineering. So in addition to free form modeling, you have the precision for precise engineering designs. Well, what about the mathematical properties of splines? Well, in the talk in the spring, I talked about functional analysis properties, H and K refinement, spectral analysis, which is extremely revealing, and the variation diminishing, and the convex hull properties that are all satisfied by splines, but not by the usual bases of finite element analysis. And today, what I'm going to do, as I said, is I'll talk about the Kolmogorov n-widths and show how that concept can be used to evaluate things. But I will do a very brief review of these three, again, for people that didn't see it. This is sort of a nice summary diagram of some functional analysis results. We started this off ourselves right in the beginning, around 2006, with a generalization, and I would say a non-trivial generalization of the Bramble-Hilbert lemma. And from that, all of the typical finite functional analysis results ensue. Now, this is a picture. This was done by Espensande and colleagues at University of Rome. And it's essentially a functional analysis as estimates that are explicit. These are 1D, but splines, most of the constructs are based on tensor products. So you can assume that these apply in other situations as well. It's a complicated picture, but let me just summarize it. What we have is the polynomial basis of the splines is going from 1 to 10. Each curve represents 1 all the way down to 10. And the continuity is running across horizontally. So as we increase the continuity of the spline basis, we go to the right. Now, good accuracy is down. You want the curve to be as low as possible. That's the optimal accuracy. So how do you get accuracy? Well, the first thing you could do is just fix the smoothness and increase P. So you'd be coming down curves like this. This would be like for finite elements, C0, linears, quadratics, all the way up to P equals 10. Okay, so you do that. Another way is to fix the polynomial degree and increase K. So you move along one of these curves. So for P equals 10, you move to the right. And you can see as you move to the right, you keep getting more accuracy because you're dropping. But notice the big gain is down here. To get the optimal accuracy, you want to increase P, higher order, and you want to take the smoothness to be as much as it can be, which is P minus 1. If you go higher, you have a global polynomial rather than a piecewise spline. So that's as smooth as you can make it, and going to maximal smoothness gives you the biggest drop, the most bang for the buck right there. And that's essentially K refinement. So that's where you get the most accuracy. Now notice, where do you get the least accuracy? Discontinuous Galerkin method, C0 finite elements. Everything else, as you get smoother, you get better. Pictorially, what's going on here, you can think of a space of polynomial degree and smoothness. And discontinuous Galerkin, of course, the smoothness is -1. Continuous Galerkin is 0. As you go to higher polynomial degree, you go with this way here. Now, with in IGA, you have all sorts of possibilities. But if you go the maximal smoothness route, as I just advocated, you go up along this diagonal here. And what you're doing is you're going from, say, lower order, 1, 2, 3, finite element type things, but smooth finite elements, to spectral methods. And this is providing a continuous pathway from low order finite elements to spectral methods. And these are function spaces that we never had in the finite element method before. And this is sort of an outgrowth of isogeometric analysis. In the area of spectral analysis, I showed you some portraits of the areas last time for splines here on the right. These are fourth order splines that are C3 continuous and C0 continuous fourth order finite elements. And what I pointed out is the spectral behavior of splines is very much what you would assume. The idea is 0 is exact here. So this is the mode number is plotted along the horizontal axis. This is just for a one-dimensional second-order operator. So you're looking at the eigenvalues and the eigenfunction errors. And this is a invariant spectrum. So you have This pertains to any number of elements, 1,000, a million, whatever. And this is just like, say, the mode in the middle, which you can see is quite accurate in respect to all quantities. And the nice thing is you have this Pythagorean eigenvalue theorem, in which the eigenvalue error and the L2 norm of the eigenfunction error and the energy norm of the eigenfunction error, they sum up in this way that is exact, and it holds for every mode in the discretization. So this is really a portrait of the discretization you might compute with. And you can see everything's accurate in the lower modes. And then you have some degeneration of the eigenvalue and the eigenfunction in the sum, the eigenfunction in the H1 norm in this case. Now you look over at finite elements, my goodness, this is a surprising picture. This is catastrophic. You have what they call optical branches of your spectrum, and they diverge with P. As P goes higher, these things get worse and worse. In fact, the black curve here is off the slide. When you add the red and the blue, it goes off the slide. The areas in the high modes are enormous. You even get pathologies in strange places in the spectrum, like here in the middle. And as a result, this really explains why the finite element method has never been successful with higher order elements for hard problems. You do hard problems like crash dynamics or blast type calculations. We have hyperbolic equations. You ping those high modes. Those areas are introduced in these high modes and they never go away. So there's a tremendous advantage over here. Actually, with these methods, with the spline-based methods, you have robustness in the high modes. You have the methods get more robust as you go to higher and higher order and higher smoothness. Just the opposite of what you see in finite elements. And again, the variation diminishing property. If you know what that is from computational geometry, it's manifested by how the control points are fit by NURBS and B-spline bases, whereas with Lagrange polynomials, the interpolatory property with higher order elements is actually a disaster. You certainly don't want that. Let's talk about Kolmogorov n-widths. What you can do with this is you can approximate the properties of finite dimensional spaces. You get approximation results, I should say, for finite dimensional spaces. And when you think of the basic functional analysis result, which is sort of an approximation estimate in various Sobolev norms, everything kind of looks the same. With it's really not dependent on the smoothness. You don't see anything here because it's asymptotic. It's only telling you what's going on in this part of the spectrum where you're very accurate. So, but the constant is, like many constants, it's a function, and it's a function of things that are extremely important to tell you about other things that are going on. So the Kolmogorov n-widths approach gives you some insight into the constants and some other things that I will describe right now. It's interesting how we got into this business. Ivo Babushka, my colleague at UT, was convinced that smooth splines were a disaster for PDEs of various order, second order, fourth order, whatever. And he induced us to look at this and do some comparisons. And as you'll see, the results were just the opposite what Ivo thought, but he was agreeable to include himself on our paper. So in approximation, think of it this way. You have a big space, okay, X, and you slap a topology on it, the X topology. And what you want to do with a finite dimensional space is to approximate X. And the best approximation is the guy in your finite dimensional space that's closest to X. So it would be Y star here. So that's just the infimum over all Yn in this space, okay? Now, in Kolmogorov n-widths, the interesting idea is to look at the worst best approximation. You look for the bad guys in the target space that you can't approximate very well with your finite dimensional space. And that gives you a measure of how good your finite elements, your discrete space is. So you have your discrete space. You have to normalize, you have to take a normalized set, because obviously if this is unbounded, there will be elements in here that are out infinity, and the infinity and the errors will be big. So you say you work with a unit ball in the big space, that's A. And what you do is you take the soup over the target, X, okay? So you take the soup over that, and so that is your worst best approximation. Now, if you like inf soups, you're going to really like Kagarov n-widths because it gets to be even better. So the n-width is the infimum over all n-dimensional spaces. You look for the finite dimensional space that is the best at producing the worst best approximation. So it's the inf soup inf. And then what you can do is, if you have an n-width for a space, and for various models and simple geometries, we know what the n-width is, we can compute an optimality ratio by looking at the soup inf over that. And it leads to very complicated eigenvalue problems. I'm going to show you some results for looking at the space over the space, essentially H5, or the unit ball in H5, the Sobolev space H5. You have to solve 10th order eigenvalue problems in order to compute these quantities. So here it is. So we are looking at the unit ball in the domain 0 to 1. This is the unit ball actually in the Sobolev space in the domain 0, 1, H5. And we're going to look at it in the L2 topology. So we'll measure error in the L2 topology. And we're going to use quartic n-dimensional spaces, but different kinds of quartics, finite elements and B-splines, smooth B-splines, C3 continuous. And if you look, what you should be comparing is at fixed n. So say for a 40 dimension 40 space with the quartic B-splines, your error would be here. Okay. And for here, it would be roughly 5 times as big. Okay. All right. So you had to solve a complicated eigenvalue problem to get those exact curves. And what we also did is we looked at it assuming maximally smooth linears, quadratics, cubics, quartics, quintics. And the target space was H1, H2, H3, H4, and H5. And what you want this plateau here to be as close to the bottom here as possible. That would be essentially an n-width. And what you see is, if you want to get accuracy in something like the class of H5 functions, you really need smooth basis functions. That's the only way you can get really high order accuracy. Okay. On the other hand, with these maximally smooth basis functions, even if your target space is not so smooth, it's say H1, you're losing nothing. And that was the surprise to everybody, I guess, especially Evo, that smooth splines are always good. They work great for the rough problems as well. Not smooth finite elements, smooth splines, or smooth spline finite elements. Okay, so let's finish up. Well, already 2:51. How much time do I have, by the way? Hello.
It's an hour altogether, but I think if you need a little longer, I think you can do that.
Okay, I'll try to be as close to an hour as possible. Okay, modeling paradigms, boundary fitted. We're not going to talk about that. Immerse modeling. So let's we'll say a little bit about boundary fitted. This is typically what you do with a finite element model. This object, it looks like, oh, that's a very nice mesh and all, but it isn't. Actually, you've eliminated features here. You have sharp edges here when there actually are fillets and doubly curved areas that are hard to mesh. Everything else is easy to mesh. But if you want to use immerse, the idea is just drop it into a box and then use immerse technology, and you have the exact geometric model in there. There's no feature removal here. So this is traditional FEA, a lot of feature removal to generate a mesh in a finite amount of time and of a finite size. Of course, now core forms technology, they are actually doing things that kind of fill in the spectrum in between. First of all, you can pick better bounding boxes that have some features of boundary fitted, and the rest is immersed. And you can even go further. This looks about the same as here, but there's sort of a ghost in this region, and I'll show you a detail of it. The ghost there is, this region is immersed in this part here. So you have the exact geometrical model in there, and that works very, very nicely. Let me show you a project that we've been working on for the last few years. It's taking imaging data of the heart and trying to solve for the states of stress in artery walls. So the data comes from coronary computed tomography angiography. The voxel spacing is about 1/2 millimeter, so we can't see all the details. But these are the types of models we get out. This was done by HeartFlow, our industrial partner that I've worked with off and on for years. And this is a portion of the aorta. You can see some of the arteries, the left anterior descending, the left circumflex, et cetera. And HeartFlow does, as the name kind of conveys, a CFD analysis of the flow in the coronary arteries. These are just streamlines. And then from the flow, Navier-Stokes calculation of the flow, they calculate what is known as the fractional flow reserve. It's essentially the pressure drop across stenoses. And what we've been working on is actually developing a methodology to analyze the stresses in the wall. So regions of interest are identified between these 2 points along a center line, as you can see. So the lumen mesh is the inside wall, and the outer wall is here. So there's presumably some atherosclerosis in this, and this is what we want to look at it. And that's the place. So we do biomechanical simulation, computational solid mechanics, isolate the lesion. And you might say, well, that region looks like a tube. Yeah, it does. But of course, you've got a bifurcation there as well over here. So could you model that as a tube? Well, you could, and you could mesh that any way you liked. But the problem is you don't know the boundary condition here. The heart is not hanging in space by a string. It's surrounded by tissue. It's encased. So all of that tissue is around there, and you don't know what the boundary condition is. So the only way to deal with that is to model it. So we put a bounding box around it and do an immerse type approach. So what we're given is we're given the lumen geometry from the CFD analysis of HeartFlow. Okay, that's immersed in our bounding box. And then we have to develop properties for the tissue that's surrounded throughout the box. And that's essentially done from Hounsfield units and other information in the published literature. It gives us, say, Young's modulus as a function of the intensity of the CTA. So these are just material properties slices. So again, we have the flow, and from the flow, we can calculate the forces on the lumen, the traction vectors on the lumen, and then we apply those to our solid mechanics analysis. And we use hierarchical refinement in 3D to mesh around the region of interest. And the technology there we use is truncated hierarchical B-splines. It's just a linear elastic model. This is just showing some of the properties of Young's modulus. It varies like crazy. You see these hot spots when you see these little red spots in this diagram over here. Those are calcifications. So you're getting all sorts of different things. This is the Hounsfield units. These are the Young's moduli here. So it's very heterogeneous over orders of magnitude. And these are some results. This is stress in the vicinity of the lumen. And we're interested in where the vulnerable plaques fail and could cause a heart attack. Now, you might say, can you get the accuracy with techniques like this? So I'll show you this result. It's an exact solution for a cylinder-like structure, sort of you can think of it as a cross-section of an artery. And this is just with boundary-fitted NURBS. It's an exact geometry. It's not surprising. You get a point-wise exact solution with this order of NURBS. And it's axisymmetric, as it should be. What happens if you immerse though? So this is our mesh. We're going to immerse that object in there. We're going to use adaptive refinement, as you see, in the vicinity of the object. The key, though, beyond the adaptive refinement, which is important, but the key is adaptive quadrature refinement. The blue here are quadrature meshes. We are refining the quadrature meshes within the elements. These are the quadrature point meshes. Those are the quadrature points in this area right here. Lots of quadrature points to get accuracy. We are also embedding a surface in there that is precisely known. And we have to do quadrature along that is precise too. So this has to be done precisely. And if it is, the amazing thing is, even with the immersed approach, you basically get axisymmetric response. You get the exact solution. You get the exact stresses at the wall. And this is just an indication of that. This is the hoop stress. That's the major stress, the tension there, plotted along these lines. And they're all the same, as you can see, and they're all exact. Another example of immersed, the problem setup is so fast. This is coming again from core form. This is dropping a complicated CAD file. This is a three-dimensional object. All these struts in there. So we just dropped the CAD file in there, the given CAD file. That took 29 seconds. Setting up the immerse problem, now you're at 1 minute total, another half minute to do it. And then you run the simulation. There's about 8,000 cubic U-spline elements here. So it's just a 20 by 20 by 20 mesh of solids, it's 3D, and you just let it go. Large deformation analysis. The whole bounding box moves with the geometry. Very, very robust. Heart valves. This was a jig that David Kamensky, one of my students here, built to actually assess bioprosthetic heart valve design. You would drop the design in the experimental jig. So we built a computational model, of course, of it too. And now we let the walls be flexible. They actually have to be. If you don't have flexible walls, you get sort of spurious behavior with the valves. So these are three different designs. This is a bioprosthetic design. This is the sort of the scaffold that holds it. And the technology is quite complicated here. It's a combination of moving mesh technology, a variational multi-scale Navier-Stokes solver, a solid generalization, hyperelastic generalization of the Neo-Hookean model for the wall. And then you have this finite deformation leaflets modeled with Kirchhoff-Love smooth shell theory. And that's all going on. That's moving with respect to the background moving mesh of the fluid. So this mix of moving meshes and all and different descriptions allows you to solve very complicated problems. This is just a comparison of the thicknesses of different valves. The surgeons like very, very thin valves because they can get them in with a catheter. You don't have to do open heart surgery. But the problem is the very, very thin valves, they flutter. And that can cause damage to erythrocytes, to blood vessels, to blood cells. So the future, quickly, computational medicine, becoming a big field. Phase fields are everywhere. Trimmed CAD, immersed, that's a phase field. Topology optimization, that's a phase field. Continuous phase fields, fracture, additive manufacturing. This is fracture. We're pulling apart a domain, elastic domain that had an initial fracture in it. So it breaks into many, many pieces. What's the mesh for that? It's this, it never changed. All the calculations are done on the original mesh. All of this is embedded in the phase field, and we've developed some theories for that. Multi-phase flows with phase fields. This is the Navier-Stokes-Korteweg equations. You can the phase field here is density, and it can become multiply valued depending on temperature and other things. What you see here is the density of a fluid domain that is being heated from the bottom. There's a cooling plate on the top that you don't see. This is the free surface. You heat it up, and these plumes emerge of hot gases that essentially form. You go through a phase transformation, and then you get droplets condensing on the top. And this is the temperature field. And you can see how fine-grained the analysis is to resolve the beginnings of the plumes. And this is sort of an animation of that. So the plumes rise up, they pierce the free surface, bingo, and then they start to condense into droplets at the top, and they fall back into the flow. So another area that's going to continue, obviously, is this integration of design and analysis, and several commercial firms that I've had some affiliation with are implementing IGA in that capacity. But the big elephant in the room lately, I'm sure everybody knows, is machine learning. And there's starting to be a lot of applications in design and analysis. I won't do a history of AI and machine learning. I'll just point out one thing. It sort of started in the 1940s as well as the finite element method. And I won't go through the architecture of neural nets and all, but we're starting to build ones that look more and more like variational methods. And this is just some of the discretizations that come out of these that I don't think are really good for what we want. I will say, though, what are people doing right now that are experts in both deep learning and the finite element method? And HeartFlow is an example. They have a real core of very strong people in deep learning, and they have products, Deep Lumen and Deep Plaque, and that's how they create these anatomies from CT. But when it comes to the fluid mechanics, they are still using finite element methods and a code technology that we developed over 20 years ago. And you still can't beat that. So they could do deep learning. They have a database of hundreds of thousands of these coronary trees analyses. So they could use that to develop a neural net for this. Maybe they have, I don't know, but you can't get the accuracy yet. So the future, what is in the future? Computers, new materials in place of silicon. We've been hearing about that forever. Maybe graphene nanotubes is a possibility. And of course, new paradigms, quantum computing, quantum algorithms. This is where mathematicians and computational mechanicians can play a role, quantum algorithms. Now, machine learning, okay, where is it going to go? That's the big question. At present, it's not competitive for forward problems in computational mechanics. Finite element methods, especially IGA, are faster, more accurate, more reliable. And there are many, many examples that I'm aware of that. However, the book is not closed. Research is going on, so there are many possibilities. And some of them are to maybe brand new methods to start to compete, but already we're seeing some that can improve finite element applications. Iterative equation solvers are emanating from this, inverse problems applications. So it's already a proven technology in model development in computational medicine, and it certainly has a future in analysis. So predictions. There are no long-range predictions that are any good, so I won't give a real long-range prediction. And the reasons why, first of all, I'll just quote Yogi Berra, whom I assume you've heard of. He said, "It's tough to make predictions, especially about the future." Indeed. And when smart people have tried to make predictions about the future, they haven't done very well. I think we can agree that William Thomson, Lord Kelvin, was smart. And in 1883, he predicted that X-rays will prove to be a hoax. He should have learned his lesson, but he didn't, apparently. So he tried again in 1895, and he predicted that asserted that heavier than air flying machines are impossible. Now, I think we can agree that Albert Einstein is a smart guy, and even he fell into this trap of making a prediction. He said, there's not the slightest indication that nuclear energy will ever be obtainable. He had to walk that back not long after. This is the one I like the best. It's William Stewart. He was the Surgeon General of the United States in the 1960s. And he asserted that we can close the book on infectious disease. I didn't know that, but once I did, I threw my masks away because the book is closed. And no more masks, and looking forward to the future of computational mechanics. Thanks for your attention.
Thanks, Tom. I'm trying to clap, and I don't know if it's possible to hear.
I hear you.
All right. So anybody, any questions? So let me ask you this. It's maybe a little bit aside from the directions you mentioned, but like you mentioned, solid fluid interaction, but how well does it work with like solid, especially like if you try to like say roll a solid on another solid?
Well, I mean, everything just depends on how you're dealing with the interface. If you take one solid and it's actually C0 conforming to another solid, you just assemble the elements, right? And you can even do that along non-matching interfaces very well. If you're talking about contact problems, that's basically is an industry built on contact problems in mechanical engineering. LS-DYNA is probably the #1 crash dynamics code in the world. And contact is everything in their applications. Things are smashing together. But even, in other areas, national labs, they design weapons and things like that. There's lots of contact problems there. So there are very sophisticated and robust technologies.
All right. Anybody? Any other questions?
Dimitri, you hear me?
Yeah.
I just want to let you know that I was also at the 64, 65 World's Fair in Flushing Meadows. I was there many times. I lived in Elmont. You just take the bus there. And I actually performed there. I was in a rock band. We backed the fashion show at the New York State Pavilion. I remember that the World's Fair was great. Yeah, I've been to Flushing Meadows several times after that. It's now a park.
Yeah, it's still there. It's still there too.
Yeah, no, it's a nice park. I have another question. So when you were working in Groton, do you remember any of the subs that you worked on or that were produced then?
Yeah, the 637 class.
With any names of people?
Everybody was scared to death of Hyman Rickover, who was the admiral in the Navy, who was in charge of the whole submarine program.
I mean, the titles, the subs that were,
there's I forget the name of the class, the 637 class, but I think I might have it on that slide I showed you.
So I'm asking because my brother spent 2 years on the George C. Marshall.
Okay, this is it was the 637 of the Sturgeon class.
Yeah, I don't know about.
It's been a long time. I don't remember.
I was just kidding. My brother was 2 years on the nuclear attack sub, the George C. Marshall.
Oh, he was an actual submariner then, huh?
Yeah. That's how he spent his time in the military. How he avoided Vietnam.
You needed a special personality. You needed nerves of steel to be a submariner.
Well, he was a steam fitter on it.
But
he would never tell or reveal what he was doing during that time. Sworn to secrecy, but you only learned later from this book called Blind Man's Bluff about what the U.S. and Russians were doing.
And they're
all the time along the North Atlantic. They were just pinging each other, trying to figure out what each of them had, their capabilities.
They're still doing it to this day.
Probably.
Yeah, that's interesting. Where you went to high school in Elmont too?
Yeah. Elmont Memorial. Where you're from, Brooklyn?
Yeah, I went to Brooklyn Tech. Yeah.
Yeah, my father was born and raised in Williamsburg.
Okay, good.
Yeah, worked there.
People from Brooklyn are everywhere.
Yeah.
Especially the sciences. I mean, I meet people every day from Brooklyn Tech and Stuyvesant and Bronx High School of Science. The 3 magnet schools for science, and have a lot of friends from those 3 schools that are still doing things today. Good.
All right. So, anybody else? Any questions? All right. Thanks a lot. It was fantastically interesting. So, very much appreciated that you could speak to us.
My pleasure. Thank you. Okay.